Lecture 35, Virtualization and Containers. We'll start off by talking about virtualization as a topic. As you can imagine, this is the last topic in the course, so we're not going to be going into a tremendous amount of detail. But there are some interesting things here that are worth touching on. And this also, in a way, serves as a nice way to review some of the things that we've talked about so far. And when we talk about virtualization, right, what I really mean is this idea of virtual machines. The goal is to abstract away the hardware of a single computer into several different execution environments where potentially we have more than one operating system running or multiple copies of the same operating system, depending on what's desired. Right? We get our choice of what we would like to make happen, given that we have the sort of virtualization environment. Most frequently in the past, one of the causes for using virtualization was this idea of like, okay, I'm a Mac user, but there's a program that runs only in Windows that I need. One way to do that was to have a virtual machine. And somehow this was like less effort than other alternatives. You might be able to configure a dual boot system, although at one point when Mac OS was on PowerPC, it was not that easy because you couldn't get a version of Windows that would run on the hardware that you had. Things get more complicated with different architectures, but this idea of having a virtualized environment to run that one program that you need, it's not crazy, right? And from the perspective of whatever operating system we have, it doesn't know that it's running on an abstraction of the hardware. It doesn't know that it's running on a virtual machine. As far as it is concerned, it's just running, on a machine. Comparisons to the Matrix are pretty apt. How would you know the difference between the dream world and the real world? Right? Okay, I'm no Morpheus, but worth a shot. So at the lowest level, when we talk about the virtual machine setup, we have the host. And the host is the underlying hardware system. The virtual machine has to run somewhere, and so it does so on the hardware, and we call that hardware the host. Above that, we have a virtual machine manager or a hypervisor. And this is the typical thing that we do, right? I guess it's important at this point to say we don't have to organize it this way, but we have a virtual machine manager, which is sometimes called the hypervisor. It's like the supervisor, but one better. And it creates an interface that looks like a host, and guest operating systems interact with their own virtual copy of the host. So your typical behavior for a non-virtual machine is shown as A on the left here, where we have our hardware. Above that we have our operating system, including the kernel, and then there's the API, the programming interface, and above that the various processes run. And over on B, we have the situation where the hardware has a virtual machine manager. It has some number of virtual machines, and each virtual machine, in this case 3, contains its own kernel, its own processes, and they are separate. As I say, this isn't the only way to organize it. It actually doesn't match what I said earlier, this idea of, okay, I'm a Mac user, but I don't need to run a particular Windows program. In that case, it would look more like A, with a smaller version of A inside the processes area. There is a virtual machine manager. I think at the time I used VMware. And so that runs as a process inside my Mac OS system. And then inside of that, it's presenting a virtual machine, which then has a Windows kernel, and the Windows kernel has processes running that use it, recognizing, of course, that there is a certain penalty for doing this in terms of performance, but we'll get there. The more common thing we have today, when it's a server in a data center, something like that, resembles what we see on B in the diagram, where we have a virtual machine manager. We have VM1, VM2, VM3. And I want to differentiate, in this case, the difference between virtualization and emulation. And we have virtualization in the case where, say, Windows and Linux are running on the same x86 64-bit architecture as guests. If instead you were doing like Android development on your machine and you had an Android simulation running, that's emulation, right? The code of the emulator is running in the x86 environment, but it's simulating an Android hardware device that has a completely different CPU. This does allow an Android app, which would not otherwise run on your Intel or AMD architecture, to run in this emulated environment, because when that Android environment issues a CPU command, we will then emulate it, which is to say we're going to basically interpret that command, figure out what the response should be, and fake that response. It's not the same thing as actually running it on the hardware, but it is an approach. And that's necessary, right? If the Android thing is expecting to run on an ARM CPU and we have an x86 CPU, we can't just issue the assembly instructions and say, all right, well, CPU, you figure it out. So that's very different. Now, an Android app, which would sort of not otherwise run very well on, say, an Intel or AMD machine, can run. The emulation operation is very slow, and if you've tried to use the Android emulator, it may have improved as compared to when I wrote this, because I wrote this quite some time ago, after having tinkered around with it before that. That the Android emulation is actually quite slow, and it's okay for certain use cases. If you're just sort of testing the workflow in your application, you want to be sure the user can log in and go to their account and configure their settings. You can use it for that, but you wouldn't use it for like validating performance or anything like that, because it's just, quite frankly, way too slow for that, and that's okay. But on the other hand, emulation is a question of what are the resource demands as compared to what is available, right? If you were trying to play a classic game that ran under, say, MS-DOS, so at this point we're looking at something that's like more than 25 years old. At this point, emulating a 486 computer, which is like early 90s, because you want to play TIE Fighter, and you do want to play TIE Fighter, it's a good game. That's very easy, right? The modern computer can do that with ease. Similarly, if you look at, say, like Nintendo Switch, they have their Nintendo Online service, and they have emulation for classic Nintendo games, NES, Nintendo Entertainment System, and Super NES, Super Nintendo Entertainment System games. And although they're quite old at this point, many of them are actually good. There's an incredible number of bad NES games, but there are still some good ones. If you want to look at some good ones, you could. We could talk about it, I suppose, if you want. You could look at, say, the Completionist channel on YouTube for that. If you want to hear about bad ones, then you're looking for the Angry Video Game Nerd. Either way, right? You're emulating on the Nintendo Switch the Super Nintendo Entertainment System that came out 30 years before, and doing that is very easy, because the computing power that the Super Nintendo had is tiny in comparison to a watch these days, even like a not smart watch, and therefore it's very easy for a modern system to be able to emulate it. But as we know, there's already this other scenario where we're trying to run an application that doesn't run, say, under your current operating system, it requires a different one. That sort of thing can be arranged, even if it is somewhat painful. And as the versions of Windows have proliferated and evolved, sometimes things don't get updated, right? Whatever program that's needed for some purpose has never been updated, so it doesn't run under a more modern version of Windows. And we have this problem sometimes at the university where we've got some software that controls a hardware device, and the software has not been updated because it would cost thousands upon tens of thousands of dollars to pay for the upgrade cost to get the same functionality, but works under Windows 10, and that's frustrating, right? Why would we pay that? It doesn't seem like a good deal. And so, yeah, in the end, sometimes what we do is decide, actually, we're not going to do that. We're going to keep our Windows XP machine because that works. Now, for security reasons, the Windows XP machine is disconnected from the internet, so it's not vulnerable to being exploited. But that kind of thing does actually happen. Yeah, there's always a risk that sort of older programs are not updated, or they would stop working under newer versions of Windows, even though there do exist some run with backwards compatibility options that can help. They're not magic. So virtual machines are a way sometimes to have an environment where, okay, we can maintain an existing version of something that would otherwise not be available. Another thing that's actually very nice about virtual machines is that you can pause the execution of the running virtual machine, and this is like pausing all of its execution, so all processes, but also whatever the operating system is doing. And this is very much like pausing a process. The current state is taken and saved, and it can be restored at any time. But also like a process, you could move it somewhere else, right? So when we pause a process, it was running on CPU 1, we can move it later, and when it resumes execution, it resumes on CPU 4. That kind of thing is entirely possible. And we can do a very similar thing with the virtual machines. If we suspend it, we pause it, then we could move it to new hardware and nothing would happen, right? It would be just as if it had always been running. I mean, the operating system was suspended, so like the clock is a little out of date and that's going to need to get updated, but it is pretty much just as it was left off. Also, like a process, right, we could clone it. Right, we'll pause execution, we will create a copy, and we'll go from there. And that's one of the ways that you could actually save on setup time, right? If you have a virtual machine image that contains your base setup, it has all your security patches installed, it has everything that you would actually want as a baseline, and then after that you just need to install whatever application is supposed to run. That's great. Just copy it. And a third reason for virtualization is protection. Guest operating systems are isolated from the host and from vice versa. If a virus gets into one of the guest operating systems, the other ones are not affected. And as with a virtual machine, it's that much easier to delete and reinstall the guest or roll it back to an earlier state. And that's actually very easy. You can just pause it, like take a copy and of whatever state has been saved, whatever files, whatever disks are associated with it, and then when you want to restore it, you just move it back from the storage location to the active location, and then you're ready to go. And another big thing that caused a push for virtualization, and admittedly this is quite some time ago, was the idea of consolidation in data centers, right? There are many servers running that could be sharing the same physical hardware. Instead of having numerous lightly used actual physical machines in the data center, you could convert them to a virtual machine, and you could run several of them on the same hardware, and they wouldn't really interfere with each other, because there exist these isolations between different guest operating systems, but also if they're not using a lot of resources, then we can save on the amount of actual hardware that we have spent money on. So that was a big thing, right? Now, we'll talk about behind the scenes. I think I gave some motivation as to why we want to do this, and why is it important, and what are the benefits of it. But realistically, I think we need to understand a bit more about how it works. And one of the key building blocks of the virtualization is this VCPU, virtual CPU. And when we say virtual CPU, we're not saying it is some sort of CPU in the matrix or anything like that, but it is the state of the CPU from the point of view of the guest. Right? The actual CPU that is executing code has its own state, just as it does. It doesn't really care whether it's executing guest code or host code or something else. It is just an execution engine. The virtual CPU is where we store the state of a guest operating system's view of the CPU. And there is a virtual machine manager that is responsible for maintaining that state. And you can think of it as being in a way like a process control block. It's a data structure, and we'll store the state of the CPU in there when the current guest is not running, and we'll restore the state when it is time to execute. So that works. But application processes, as we know, run in user mode for the most part, and then when they need to call on the kernel, then they go into kernel mode. And that's sometimes a bit of a headache. right? The guest operating system is intended always to run it in user mode, but it will eventually want to do some things in kernel mode. Okay, doesn't sound too bad overall, but we need some more support to make this happen, right? When we request to go to kernel mode, well, we're not really doing that, say in the guest operating system. We're going to virtual kernel mode. Now, if a guest attempts a privileged instruction, it generates a trap because it's in user mode, and so it's now trying to issue an instruction that requires kernel mode, but we're in virtual kernel mode and not real kernel mode. If that's the case, the virtual machine manager will pick it up and decide what to do. And it can either emulate the operation or just carry it out, depending on what it's going to be. So if the user process wants to execute a privileged instruction, right, there is a trap. The virtual machine manager will emulate the action if necessary, update the state of the VCPU, return to the user process as before. So non-privileged instructions can just execute natively on the hardware, so they are effectively as fast as they would be if they were executed outside a virtual machine. So there isn't a lot of overhead associated with it for those kinds of instructions. However, with trap and emulate, the privileged instructions are more expensive because it's not just a question of switching from user mode to kernel mode. We switch to like virtual kernel mode, and then there's another trap, and emulating or simulating, if you will, the instruction that was supposed to be executed is more expensive than actually just directly executing it. So if you've wondered a bit about why virtual machines are slower than non-virtual machines, this is a big part of why. Yeah, with trap and emulate, there is this extra overhead. Hardware can assist with this, right? Hardware designers have been kind enough to offer this idea of sort of keeping track in hardware, the idea of virtual user and virtual kernel mode, which relieves some of the responsibility the virtual machine manager has of keeping track of all of those things. And so when we talked about the mode bit in earlier lectures, distinguishing between user mode and kernel mode, the truth of the matter is it's more complicated than that now. It's more than one bit because there are more possible states. Now, there is a catch. And one of the things that will make our life difficult is how do you know if something is a privileged or a non-privileged instruction? For some of the instruction sets that exist, that's pretty easy. There's a clear distinction between what is a privileged instruction and what is not. x86 is not one of those things. x86 does not have, and its descendant x86 underscore 64, the 64-bit extension of it, is not one of the instruction sets where we can clearly delineate these are the ones that are privileged and these are the ones that are not. Without editorializing too much, there were a lot of decisions that went into things like the x86 architecture and the C programming language and the design of Microsoft Windows and what have you that make no sense if we look at them with what we know today. But they fall under, it seemed like a good idea at the time, or at least it was appropriate at the time. The x86 architecture started back in the 1970s, and we can hardly fault the designers for not being able to anticipate what would happen 40 years later. As a Danish proverb of disputed origin says, making predictions is hard, especially about the future. I don't know what the original is in Danish. Sorry about that. Or undskyld. Now, here's an example just to illustrate the nature of the problem. There's an instruction popf that illustrates very well the issue. It loads the flag register from the contents of the stack, and if the CPU is in kernel mode, then all of the flags are replaced by whatever is on the stack. If it is in user mode, then not all of them, only some of them. Getting into which ones are replaced is not necessary for the sake of this explanation, but we should be aware that that is actually a thing. And so no trap will be generated if the popf command is executed in user mode because, well, maybe that's actually what you wanted. You just wanted to execute the user mode one where we're only popping the user modifiable flags, but we don't know. And so trap and emulate won't catch this and it won't react. right? We won't notice that, oh, actually we were supposed to do something there and we didn't, because it's hard to tell whether this was intended as a privileged instruction or whether it was not. So what do? Well, we say that all instructions that fall into this category are special instructions because they require special handling. And to get around this problem, there is binary translation. And it is more or less exactly what it sounds like. If the guest VCPU is in user mode, the guest can run its instructions as it is. If the guest VCPU is in kernel mode, the guest believes that it's running in kernel mode even though it's really not. And if that's the case, the virtual machine manager is going to actually inspect every instruction before it actually gets sent to execute. If they are regular instructions, they can just execute as they are. If they are not, if they are special instructions, then they have to be translated to something else. They're replaced with alternative instructions that give the same result. That's complicated, and it is a little bit slow, but it is doable. So when the special instruction is issued, we will translate it, we will execute the translated version, we will update it, and then we will update the state of the VCPU, and then we return to user mode. So we get there by the same route, even though there is a bit of a detour, right? We do have a performance decrease as a result of having to examine and replace these instructions and determine what to do in that situation. For the most part, the alternatives are well known. So if we see a popf instruction, we know, okay, in that circumstance, we execute the following n instructions to produce an equivalent result. So we don't have to think it up on the fly, but there is still replacement, and the replacement, it might be multiple instructions to produce the same result. So it's not always going to be just replace this one instruction with an equivalent other instruction. In fact, it is very likely there will be other instructions, so it is certainly going to be slower. And of course, inspecting every instruction before it's actually issued is overhead, it is work, and needs to be dealt with. So yeah, we do have a performance decrease, again, as a result of having to examine and replace some of the instructions. Keeping in mind that unlike the emulation one, this doesn't apply to every architecture. It only applies to architectures that have so-called special instructions. The unfortunate part for us is it is the popular architectures that have special instructions. And so if we want to look at the empirical test of is this being used in industry, is it good enough? I'm going to argue yes. The performance of this binary translation seems to be adequate. There is pretty widespread adoption of virtual machines running x86 64-bit hardware. So although we acknowledge there is a penalty and we acknowledge it is a little bit slower than running on native hardware or bare metal as it's sometimes referred to, I think, as we say, if the performance were inadequate, people wouldn't adopt it, right? People would say, yeah, it's too slow, it's not ready yet, we need to wait. So additional hardware support obviously helps, and it does make virtualization work a lot better than it would have. In 2005, Intel added some virtualization support to their x86 chips, and AMD did the same the year following, changing, as I said, this idea of dual mode kernel and user processors into multi-mode operation, which allows for just more options. If the guest tries to access a virtualized resource, then the virtual machine manager can take a look at that. And the virtual machine manager can do lots of stuff: enable host mode, define guest characteristics, switch to guest mode. All of it really makes things much, much faster. So that gives us a background now on how does virtualization work in terms of managing the underlying hardware. But we need to talk about sort of what's the impact. And the short version is, things get complicated, right? There's more demands on resources, and we'll consider just briefly some impact on scheduling, on memory management, on I/O, and, disk specifically. So even if there's only one CPU in the physical machine, virtualization presents one or more virtual CPUs to the guests. And given whatever machines you want, you can dedicate things accordingly. Right? So guest system is allocated some number of CPUs, depending on how you choose to configure it, and it could be anywhere from 1 to all of the CPUs in the system. The challenge really is how do we schedule the virtual CPU's operations on the physical CPUs, so we are adding another layer of scheduling, recognizing that a thread might be the virtual machine manager that wants to do work, or one of the threads belonging to a guest. Now, the guest system, as I say, is configured with some number of CPUs, and if you had a 4-core system and you assign 1 core to each of your 4 guests, then there wouldn't really be a lot of headaches here in terms of scheduling, because as long as there's enough physical CPUs in the system to meet the allocation commitments, then we have no problem. We just match each virtual CPU with its corresponding physical CPU and we're all set. But that's not likely, right? If the resources are fully committed, there are n virtual CPUs allocated, then it gets a little bit more interesting. The virtual machine manager doesn't usually need a lot of CPU time on its own, so it could basically steal some cycles here or there when a CPU is idle, or just taking a little bit of time as it's necessary to do its work. And it's okay if it runs on CPUs that are not busy, or alternatively, if it just takes sort of evenly from all the CPUs, then that is fair, right? It's as if the CPU is a little bit slower than it actually is from the point of view of the guest operating system, but it's not interfering with anything. Okay, but that's not likely. What's more likely is the system is overcommitted. There are more virtual CPUs than physical ones, so you have 4 guest operating systems on a 4-core system, but you say, listen, everyone can have 4 CPUs configured. That way, if they need more CPU time and the other CPUs are not busy, they're not just sitting idle. Because that's one of the risks, right? If you have 4 guests, each with 1 dedicated CPU, there is the possibility that 3 of the guests are not doing anything right now, and one of them is running at 100% CPU and wishes it could have more, and the other CPUs are just sitting there, waiting for work to do. So more likely, you want and will have this overcommitment situation. More virtual CPUs than physical ones. So you could have 16 virtual CPUs, but only 4 physical ones, let's say. The virtual machine manager has to figure out a way to map those virtual CPUs to the physical ones based on whatever scheduling strategy is going to work. And it's just the same concept as scheduling processes and threads as we've discussed before. We can use any one of the scheduling algorithms that we've discussed earlier, and we'll recognize that the guest operating system is going to do its own form of scheduling, so it's going to say, this is the thread I want you to run right now, and we are deciding, say, which of the guests is running. How do we make that fair, or how do we respect the priorities between different guests? All of those things are very similar to the scheduling algorithm problems we've seen before, so there isn't really a whole lot that's new here. It's just kind of an interesting discussion. Whatever we expect, right? There's going to be some differences between the view of the world from outside and the view of the world from inside the guest operating system. The expectation of the guest operating system of, say, certain time deadlines becomes inaccurate, right? If the scheduler in the guest operating system thinks a time slice should be 50 milliseconds, just making up a number, sort of don't read anything into that, that might not actually be the real time slice when it comes to actual time spent executing on the physical CPU. It could, in fact, be significantly longer because we have sort of switching out between the different guest operating systems, and so the amount of time that is taking place in reality is longer. That's not usually fatal. It can be a little bit frustrating to the users. It can cause the system clock to get out of whack, and one solution to that is like you install in the guest operating system a little utility that makes it easier for the virtual machine manager to effectively update the current time from the point of view of the guest operating system. That kind of thing is minor, but it is a problem for anything that is like a real-time operating system or a task that has a hard wall clock deadline. It is frustrating. So virtualization isn't always ideal for situations like that. It's not to say you can't use it. It's not to say that it's never going to work, but it imposes certain constraints, if you will, on our implementation and on what resources are committed to a guest operating system. We'll also talk about memory management. And virtualization, of course, makes the memory problem worse because, well, every guest operating system is taking up space in addition to the processes, right? The processes take up whatever memory they need to get their job done, and each operating system requires its own amount of memory, and so if you're multiplying that by 4, we are potentially looking at quite a lot of memory being given over to operating systems. The problem is, of course, similar to what we talked about with scheduling CPUs, in that you can choose like how much memory you want to issue a guest operating system, right? You can have, say, in your machine 32 gigabytes of RAM, but you can say, all right, guest operating system, you have 8 gigabytes to work with, and it will do so accordingly, and that prevents RAM from getting overcommitted. But of course, you don't have to do that. You can make each of them think they have as much RAM as is available. And the guest operating system, if you will, is unaware that it's a virtual machine, so it thinks it controls memory and page management and stuff like that. But in reality, the virtual machine manager is responsible for having a nested page table that retranslates the guest's page table to the real physical page table. The virtual machine manager can then do double paging, which is, it has its own page replacement strategy, and it tries to help out the guest. The problem with this is that the virtual machine manager doesn't really have much insight into what the guest is doing, and this can be quite inefficient because, yeah, we're guessing, and there's a lot of possibility that we're like guessing wrong, right? And similarly, like a lot of possibility that we disagree about what to do here. So that strategy is kind of inefficient. The next idea is to effectively install a device driver in the guest operating system that allows the virtual machine manager to tell the guest a bit more about what to do. You don't have to do this, but it can be very helpful. And if we do choose to do this, right, we are effectively adding some extra software into the executing virtual machine that allows the virtual machine manager to submit requests as if it was a process. So when that happens, we'll actually look for a balloon memory manager, and what it's going to do is basically request a lot of pages. It requests a whole bunch of empty memory and asks the guest to pin the pages in physical memory, which will make the guest think that the memory is in short supply, even though it's not really in short supply. It's just being used by other guests, and it makes the guest think that memory is in short supply, so we'll try to free up memory. The virtual machine knows that the actual memory that is requested is not real, and it can treat it as if it's empty, and that being the case, it does allow allocating that memory to other guests. And when memory pressure is lower, the balloon pages can be deallocated, allowing the guest to feel as if it has free memory. So it's kind of like putting pressure on the guest, memory pressure on the guest, to encourage the behavior that you want. Is it always going to work? Maybe. It's kind of interesting. Another idea is duplicate detection, and the idea behind that is to look and see if a particular page has been loaded into memory more than once. This is obviously much more likely if guests are identical, that is to say you're running 2 copies of Windows 10 as your virtual operating system, or 2 copies of Ubuntu. If you have 1 copy of Windows and 1 copy of Ubuntu, it's very unlikely that there will be a lot of pages that are in common between them. But anything that we can do that would reduce the number of pages that are taken up by the operating systems is quite beneficial. It can be a very significant savings because, well, if you're running 10 copies of Ubuntu or something, there's going to be a lot of stuff that is very similar between them, if not exactly the same. And so reducing from 10 times the number of pages to maybe 2 times the number of pages is required for the operating system is a huge savings, and overall you'll be happy to take it. And a hash value is usually used to sort of get a quick assessment of whether 2 things are the same, right? If we look at, say, a page of memory, it's 4K, doing the bitwise comparison will of course work, but it's slow. So if you do a quick hash and they produce the same value, then it's at least a chance that they are the same. And if that's the case, then you do the detailed comparison. If not, then yeah, don't treat them as identical. But if so, then yes, we could actually save some memory that way. And as with when we say fork and create a new process in Unix, what we're looking for is the copy on write behavior, which is we'll keep track of which pages are marked as copy on write, and if the page is in fact copy on write, then we know that if it's modified, we take a copy, we do the modification in the copy, and then there's no need to duplicate unnecessarily, but changes are not accidentally propagated where they shouldn't go. Also talk about I/O devices, and unlike CPUs and RAM, guest operating systems are very likely to tolerate the fact that I/O devices change periodically during operation. Right? Weird things happen if you try to change the amount of RAM in your system during execution. You shouldn't do that. There's probably a Linus Tech Tips video about like what happens if you open the case and pull out a stick of RAM. I haven't searched for it, but I'm sure that's the kind of thing they would do. Hardware I/O devices are of course different, right? Like you plug in a USB drive, you move in range of a Wi-Fi network, suddenly something becomes available that wasn't there before. So it does make it easier to add and remove devices from a running operating system. And the virtual machine manager, of course, gets some choice about how to allocate devices. Right. One way is to dedicate devices. So you connect a USB drive. You can say, okay, it's allocated to one guest in particular, and others don't see it. In other cases, like for network, let's say, the virtual machine manager provides a driver that's just translating commands from the guest operating system to the actual device commands. So that allows all of the guests to share, say, the same network connection. Does it work? Sure. And then, of course, there's disk. And a typical approach is to create a disk image, and the disk image contains all the contents of the root disk of the guest. And this is typically treated as one big file, although you can split it up to manageable sized chunks. And as far as the guest is concerned, it has full control over that whole disk. The guest is totally unaware that the disk is really just a file inside another system, and this does, of course, make it easy to move something from one virtual machine to another, or to another physical system if we wish. Okay, for all the talk about virtual machines and virtualization and what have you, there's been a trend away from it in recent times. And it's not to say that virtual machines serve no purpose, and there are still a lot of virtual machines out there. But what I actually want to talk about to close out this topic is containerization. And pictured here are a bunch of shipping containers. There's some interesting books about the rise of the shipping containers in sort of the post-World War II period, and how the dimensions of the shipping container dictate a lot of things about life, and how 90% of everything that you've ever had in your hands was at one time or another in a shipping container. It's just kind of how it works. So we'll talk about containerization. And to get there, I want to give you a little bit of background about it. Containerization gives us a lot of this advantage of virtual machines, but a key distinguishing factor here is without quite as much overhead. And so we'll talk about how we got here, and then we'll go into a bit more about it. So the thing about it is, like, it used to be if you wanted to run an application as a service on a server, you would do a manual install, right? So you get a physical machine, and then you get log into the operating system, and you run a script at best, or complete a bunch of manual steps according to some documentation at worst, to manually install it. And if you're lucky, then you can run a make install command maybe, or make to build it after running a configuration script, and eventually you get a running application, and you can say, aha, all right, we're ready, it's working. This obviously is error prone. It's possible for things to go wrong across different machines because they have different things installed, they have different libraries, you're missing some necessary library, some dependency. I almost said prerequisite. I've been spending too much time thinking about academic advisor things. You're missing something. So for that, one of the solutions that was offered was this idea of package management. And package managers are very useful in that they go out of their way to install the dependencies that you need, where you can say, all right, the dependency for our particular package is such and such XML parsing library, and then the package manager knows that. It's responsible for identifying the version of the package that you need, downloading it, installing it, and it really automates a lot of the work of finding the dependencies, installing them, configuring them, and then doing the same finally for your application. It's good, but it's not perfect. One of the problems that we face with this is listed there as RPM, jar, DLL hell, which is you can have different applications that require different versions of the same library, and those versions may be incompatible. If that's the case, it makes it very hard to actually run them on the same machine, and you can easily end up with a big headache. And sometimes the headache is at runtime, and sometimes you only find it out when you're actually trying to execute the code. Sometimes the problem is at least identifiable at compile time or install time, where it refuse to install the application because it cannot satisfy all the prerequisites that you want. And that's painful, but it can happen. And then we have virtual machines, and we've just spent a good amount of time talking about virtual machines, so I don't have to sort of repeat the whole idea behind them. But the idea of containerization would be to reduce the amount of overhead, right? To move from the virtual machine approach to saying, well, the container has some structure in it, it has some stuff going for it, but it's not as complicated as running an entire guest operating system. So let's look at the diagram for it. So on the left side of the diagram, we have our virtual machine, and on the right side of the diagram, we have the container thing. And so instead of having a separate guest operating system for everything, we have now a container engine, and the container engine provides the isolation guarantees between the different running applications. It makes it seem as if they're an operating system all by themselves, and allows them to have their own favorite versions of libraries without interfering with one another. And containers run using this container engine. The container engine calls to the underlying operating system as is necessary to make the various things happen. And so when the container is built, it's built according to a specification, and a specification file says what libraries, what operating system it's based on, what things are necessary to actually assemble the container correctly. And this can be non-trivial depending on what you want and depending on what you need, but it can also be very simple depending on what you're looking for. And so in this case, you can think of a container being deployed, it's sufficiently isolated, and it will share in read-only mode whatever it needs. And you can think of it as being a very lightweight virtual machine. It doesn't entirely replace a virtual machine because everything is running on the underlying operating system, so it's not quite the same as, I have a Windows program that I want to run under, say, Mac OS, and I can just make a container that contains the application that I need, but it does work for many different things that are going to run on the same operating system. So that's kind of the trend. It is a very efficient way of allowing virtualization, but we are limited by the fact that container applications can only run on hosts with the same operating system and the same virtualization features. It's okay. For a lot of what we need, we're running web services, and they were all going to run under, Ubuntu anyway, so why not? However, as I say, there's still a place in the world for having a virtual machine to run certain things that you need. All right, this closes out our somewhat lengthy discussion on the subject of virtualization. It does provide at least a little bit of an opportunity to sort of see where things are going and see what's new in the world of computing, and see how operating systems, as they currently run, are a little bit more complicated, at least some of the time, than just running directly on hardware.